Hi, it's Terry Denery of the MathWorks. So in this video, we're going to talk about multi-input, multi-output systems, right? We call them MIMO, right? And it's really a, kind of, I'll say probably the final piece I want to talk about with regard to comparing PIDs with a feed-forward approach. It turns out feed-forward actually is amazingly helpful to control multi-input, multi-output systems. So anyways, our example is this robot. We'll see that there are 4 axes of rotation or 4 degrees of freedom, each driven separately by an individual motor. So there's 4 motors being controlled here. Okay, and if we look at the model, um, here's how we're doing. And again, it's beautiful how well this example will work. And so the line is blue because they're basically a yellow command signal and a blue response, and the blue response is right on top of the yellow, and so therefore it looks like a blue line. All right, so we've talked about that as a good sign in previous videos. Okay, and so let's see, let's take a look at the control for this. Let's do it this way. All right, they were commanding position for each of these degrees of freedom. You'll see the inputs for the 2 top actuators, the turntable and the bicep motor, receiving a signal with the underscore PVA being position, velocity, acceleration. And so we're commanding all 3, which essentially commands the motion trajectory that we want. And that this algorithm, actually let's just kind of show it, which is based on the SimScape multi-body blocks, is in what they call the inverted mode. Oops. And therefore, it's taking a motion request, and it's going to tell you what the forces or the torques are required to do this, right? And so that's our calculation of our feed-forward torque right there coming out of that model. And that we then, of course, employ some feedback as well, where we'll take our command in motion, compare it with the feedback, essentially take the difference between the two to create an error, and then we'll operate on that error with a PID algorithm, right? And so the summation of feed forward plus feedback will be the torque delivered to each of the actuators, right? Now, we'll see for each of these degrees of freedom, I set up this gain, which multiplies the feed forward piece, and it's called FF on, right? And so I merely set it equal to 1 if I want to include it, and I set it equal to 0 if I do not want to include the feed forward term, right? And so anyways, what I'd like to do is turn it off right now, right? And so I'll go in here and I'll double click on that, and we've just set FF on to 0, right? And so this time, I think I'll run it from the scope. All right, so here's where we did so beautifully. And let's hit run again. And you can see some divergence now taking place between the yellow and the blue, but really not so bad. And let's just look at the animation and just kind of judge it visually too. So all that looks really, really good. And I'd say more likely than not, anybody who's developing a robot like this, they'll probably be pretty happy with that performance. So again, PIDs are amazingly good. It's an amazingly good idea that has a long history of success, and we're kind of seeing why, that it can kind of handle a sophisticated problem like this pretty well. All right. So this top one that kind of shows that divergence, I did measure the error. Error can be a little bit misleading, and I do want to just comment on that. In that, there's a little bit of a lag, of course, too, and so, it can be kind of a tricky thing to really define what your requirements are for accuracy. And so the position envelope that this thing moves through probably exceeds I'll call that envelope by something far less than the 4 degrees that we're seeing right here. But again, it's a judgment call, and what you define as good performance, can is almost always a very personal choice. All right. So, anyways, but where I want to go with this now, and you can see the commanded trajectories. They're all set up right here for each of our 4 degrees of freedom. You'll see I parameterized in what I think is kind of a cool way. That these are smooth transitions. And I essentially created P, I guess I call it for period, but the transition period in each of these examples could be 1/2 the value that I set for P. And the start time is simply, kind of creating that sequence that we saw in the visualization. Uh, and so anyways, what I want to do is make P smaller. So let's make P equal to 0.5 this time, so it's 1/2 the value it did have. And let's run the simulation again. I think I'll run it from here. I'll probably run this in playback. But even as we run this, I'm already seeing a little bit of that vibration. Right, so let's play it back though. Okay, and the scopes are always a good place to go measure that vibration. And definitely seeing it, for example, right there on this axis, which is, what's that? That's the forearm motor, which will be the 1/2 from the ground. Should be 1, 2. That's that one right there. And I'm going to slow it down on the calculation now. So let's maybe run it at like 0.18 of real-time speed. All right, so absolutely seeing some oscillation there. Again, some oscillation. And I'd say you're becoming hard pressed to say that that would be okay. But again, it's your machine, and you should make the choice. All right, and I think I'll do this one more time, and I'll make P equal to 0.1 this time. And let me just run it from the scope, and then maybe we'll look at the animation. I think I'll also only run this with P equal to 0.1. I think the whole movement's done in like less than half a second. So it's changed our runtime as well. And we'll get a little bit better resolution on our scopes. All right, we're definitely seeing big error this time. All right. Again, we'll rerun that. Yeah, look at all that. Crazy oscillations. It's really not good at all, right? And probably a number of ways you might fix it, and there absolutely are some kind of good methods for orchestrating what I call system tuning. I think our tool for it at MathWorks is called System Tune. But it turns out that turning this feed forward on, set it equal to 1 this time, it's a pretty good way to do it too. All right, and so let's hit run. Again, we're watching it at 1/8 the speed. Okay, and it's beautiful again. There you go. And I check one more thing. I check, make sure my actuation. Um, is available from my chosen actuators. You know, these are the torques in Newton meters. I'd imagine our motors will be able to deliver uh, torque on the level about, oh, what's their maximum one? This one here, we're getting around minus 20 Newton meters. May or may not be able to do that. Anyways, um, you know, one way of, and I have colleagues who are real, you know, intense, kind of serious controls folks, who kind of describe what I'm doing with feed forward is that they'll say, "Oh, you're removing essentially the cross coupling," you know, and that, I go, "Oh, that's what that's an interesting way of describing it." But it, you know, that I think it's a useful way to describe it too, and I certainly have no objection to that description. But to me, as a mechanical engineer, you know, the more fundamental thing is that I'm taking what I know, I'm taking, and I'm controlling the things that I can control. All right, and so I'm taking what I know is that I know the mechanics, I know the mass, you know, the the geometry of the parts, the materials they're made of, and therefore the masses and inertias that I'm moving around. And I'm commanding trajectories to be very smooth so that I'm not making any impossible requests. And I'm overall optimizing the performance of the system because in this case, you know, maybe this is a machine that helps me build things, and therefore I can build more if I can run it at faster rates. All right, and there's almost always advantages that can be had at these faster rates, and those faster rates are made available because you're doing multi-input, multi-output. You're executing it extremely well because you're using a feed-forward approach. All right, thank you.